So, you are discussing about the Weiss model of ferromagnetism. Weiss model of So, in this model basically this internal field was taken, is called molecular field. So, this field, and if we apply field B A, applied field, external field. So, that is the total field that permanent dipole moment will experience. Okay. So, whatever the paramagnetic formulas we have derived. So, in that formula if you replace this that B with this B A plus B M, and then that will be valid for ferromagnetism as per this Weiss model. So, then we have put the B A equal to 0, means external field equal to 0, and then whatever we will get, that is the because of internal field, molecular field, and this molecular field was taken by Weiss as a BM is proportional to magnetization, and this proportionality constant is lambda. So, lambda is basically shows the strength of interaction. So, interaction of what? So, this, as I mentioned, this dipole moment, permanent dipole moment, they interact with the neighbors others dipole moment. So, as if these other neighbors dipole moments have influence on this dipole moment, and that influence is expressed, that dipole interaction is expressed by this molecular field. So, and what we have seen that that two expression we have derived, this one is ms m by ms that is below function alpha. Okay. And so, if you plot this, if you plot this below function, so let me plot just one half. Okay. So, this it is basically like this. Okay. And this is a function, this is the m by ms, and this is the alpha, this is the alpha as a function of alpha, this is the Bj curve, and that another expression we got, that is for alpha. Alpha was what was that alpha? Alpha was Gj j mu v, right, and then your magnetic field B. So, B A equal to 0. So, BM, and then BM is replaced by lambda m divided by kBt, right. Now, from here we got this m by ms m by ms equal to what we got, this kb t alpha divided by g j j mu v square, and then that was lambda. Yes, because for ms this one n will be there, ms is n g j j mu v. I think that we have last time I have derived this. So that so these two equation, okay. So m by ms is function of alpha bj, and this m by ms this function of alpha. So the solution has to satisfy this both equation. So solution will be the intersecting point of these two curve, So if I have drawn this one, if I draw this one, so this, if I take, it's not straight line, so it will be straight line. So that is for some temperature, and then other temperature, so this curve for no, I think I have to draw properly straight line. Okay. So all this curve at alpha equal to 0, so is intersecting with this curve. So in this case m is 0, alpha is 0, so we do not have interest. In other case, so for this, say this is for temperature, say T1, this is T2, this is T3, T4, T5, T6, etc. So here you can see that here T2 is basically it is the gradient of this curve, bj curve, right. So it intersect at alpha equal to 0. So above at higher temperature than T2. So here basically we have plotted this one for different temperature T1, T2, T3, etc. So this above this T2 higher temperature, T1 is higher greater than T2. So it is not intersecting this curve, but below T2, T3 is less than T2, T4 is less than T2, etc. So we are getting intersecting point with this curve, right, this curve. So other side also will get negative value, because these are symmetric curve, So I have not drawn that part. So here, so this T2 is basically, we tell this is the critical temperature or Curie temperature, right. So above Curie temperature there is no magnetization, but below Curie temperature there is a magnetization, you can see there is a magnetization, right. So these are the magnetization value, m by ms value. So this magnetization, even without external magnetic field, we we are getting magnetization, and these are basically called the spontaneous magnetization without external field. The material which is showing the spontaneous magnetization. So, that material is basically this ferromagnetism, okay, ferromagnetic material. So, from here one can basically draw. So, I can get m by ms value for different t value, So, what we are seeing that this that you know that when alpha tends to infinity, so what we will get this Bj alpha, that function is basically 1. So, in that case you will get this magnetization m equal to ms, that spontaneous magnetization you will get, that is the equal to ms, means saturation magnetization, it is saturation magnetization. So, you will get higher value, you will get higher magnetization, and that happens alpha tends to infinity means this is the alpha tends to infinity means t tends to 0, right, t tends to 0. So, here t tends to 0. So, at this you will get maximum so you will get maximum spontaneous magnetization. Now, if you plot you see alpha is higher mean temperature is lower. So, you are going towards the lower temperature, So, this value are very their separation are very small. So, for lower temperature you will get so this basically you see this slope change is very small here, and the slope change is here in this area it is higher. So, that slope basically depending on the slope this value is decided, because slope is this by this, right. So, whatever the way slope is varying so that one can show it is varying like this. So, if I plot here in this direction t, so with respect to this Tc, with respect to that Tc, okay. So, this value is basically 1 and this value is basically 1, right, and then you just take different value, okay. So, between 0 to 1. So, this is the variation of spontaneous magnetization without applying any magnetic field, external field. So, this is very sensitive to the temperature, spontaneous magnetization is very sensitive to the temperature and it varies like this, okay. And one can show basically after proper calculation, proper form, that probably I will show you just. So, here from here what we are seeing from Weiss model, we are seeing that this magnetization, spontaneous magnetization exists in the ferromagnetic material below a certain temperature, that is Curie temperature, that is Tc, Curie temperature. Above Curie temperature, so magnetization is 0, above Curie temperature magnetization is 0, right. So, above this Curie temperature, if you apply magnetic field, then what will happen? If we apply magnetic field, then what will happen? So, that if you want to find out, then you will see that it behaves like paramagnetic material. So, basically in case of ferromagnetic material, below TC behave as a ferromagnetic material and above TC it behave like a paramagnetic material. So, this the TC is the basically phase transition temperature. TC is the basically phase transition temperature between the ferromagnetic phase and paramagnetic phase. So, ferromagnetic material have two phases, one is ferromagnetic and another is paramagnetic, and this is the phase transition temperature. Okay. So, this as I mentioned that TC the T2 equal to TC. So, how? So, this TC is related, basically it is related with this lambda. TC is related with this lambda. It depends on the interaction constant, interaction energy constant. Okay. So, how they are related, that if you want to find out. So, what we have to find out, that at this temperature T2 equal to Tc, at this temperature the gradient of these two, gradient of this will be equal to the gradient of this, okay, at alpha equal to 0. So, gradient of this is obviously is this a kV, this part, gradient of this is will be this part, right. This is the gradient. Now, this will be equal to the gradient of this one, okay, and this we are considering at alpha, considering at alpha is very less than 1 or alpha tends to 0, alpha tends to 0 at this point, right, alpha tends to 0 at this point. So, when alpha tends to 0, alpha tends to 0 or alpha is very less than 1. In this condition, this Bj alpha, that Bj alpha one can show, it will be, I think, j plus 1 alpha divided by 3j. One can show this if alpha is very less than 1, this that will be, yeah, yes, that will be this. Okay. So, I think I can show you. So, basically yes, how I have got it. So, let me show you. I think this you have to use Taylor series, but somehow it is not displayed. I need to display, but somehow it is not displayed. Anyway, you know this cos hyperbolic, we have cot hyperbolic x, right. So, it is Taylor series if x is very less than 1. So, this is the 1 by x plus x by 3 plus other term is there if x is very less than 1. So, one can keep up to this. Okay. Okay. So, using this approximation, so Bj that you know 2j plus 1 by 2j cot hyperbolic 2j plus 1 by 2j alpha. So, 2j plus 1 by 2j alpha, that if you take x, so you can cot hyperbolic x, it can be replaced by this. So, another term was this minus What was the another term? Minus 1 by j cot hyperbolic alpha by 2j, 1 by 2j cot hyperbolic alpha by 2j. So, here alpha by 2j can be taken as x, and you can get this one, that you can replace with this one, and then if you proceed, then you will get this. So, if possible I will show you sometime. So, just if you use this one, so that is basically now in this condition this m by ms is this, right. So, this gradient will be j plus 1 by 3j, right. Gradient for this at alpha is very small, alpha tends to 0 at this point. So, it will be j plus 1 by 3j. So, this will be the gradient, right. So, this gradient at alpha equal to 0 or alpha tends to 0 at this point. So, this will be equal. So, if you equate them, and where it will be equal. So, this gradient we have taken at t equal to T c. So, this here you can write T c. So, I think what to write here I can write. So, what I am getting kb gradient kbTc divided by n. Let me write this one mu square, okay. Just mu square, let me write mu square or mu j square, whatever. If I write mu square or mu j square, I can write. So, mu j is g j j mu b, and then lambda, that will be equal to j plus 1 divided by 3j, right. So, from here you can get T c, you will get T c equal to j plus 1 n mu j square, right, n mu j square lambda by by 3 j kb, right. So, that will be the T c, and now here actually j is there, j square is there. So, one can remove this j square. So, in that case I have to write this on mu j explicitly. So, what I can do, so here I can write g j square, here I can write j, and then I can write mu b square, then lambda, right, mu b square and lambda. So, this j will go, one j is there. So, in this case what yes. So, this T c we got as a so this now T c equal to n, then this we write as a mu effective. You remember that P effective, this the j plus 1 g j square mu b square, right. So, that is basically we can write mu effective square and this effective Bohr magneton number, that is P effective earlier whatever we have discussed. So, there that P effective was square root of j plus 1 gj right. So, now that I have included including mu v. So, this mu effective and that will be here, it is mu effective square into lambda divided by 3 kb right. So, that is the TC. Okay. So, now here you can see TC is connected with this strength. So, as I told you that I will show how to calculate this for alpha is very less than 1. So, this the Bj value will be this. So, that here I have just I have calculated. So, you have to take Taylor series cot hyperbolic x, right, as I mentioned x is very less than. So, this one can take this. Now, Bj you see here just explicitly I have put this for all cot hyperbolic value, and then from there I am getting j plus 1 by 3j into alpha. Okay. So, this series I think these are very important to know, this trigonometric hyperbolic function and their relation and the their Taylor series. So, it is very simple, you are familiar with the trigonometric one, but we are not much familiar with the hyperbolic function, but here you know just so if you know sin x cos x, sin hyperbolic x or cos hyperbolic x, you can find out if you replace x by ix. If you replace x by ix, then from sin cos you can find out sin hyperbolic, cos hyperbolic. So, and there in that case to satisfy these two exponential form. So, this sin ix is equal to I sin hyperbolic x, cos ix equal to cos hyperbolic x. So, reverse is sin hyperbolic ix equal to I sin x, cos hyperbolic ix equal to cos x. Okay. So, if you know this sin cos tan that relation, sin cos if you know, then you will go know this tan cot sec cosec. Okay. And there if you replace x by ix, okay, and you just remember this sin ix equal to I sin hyperbolic x, cos ix equal to cos hyperbolic x, okay, and reverse is sin hyperbolic ix equal to I sin x, cos hyperbolic ix equal to cos x. If you just remember this part, so from trigonometric function you can easily get the hyperbolic function, and these are the Taylor expansion, Taylor series, Taylor expansion, right, sin x equal to this. So, if you replace this x by ix, you will get sin hyperbolic x. Okay. You just check it. So, similarly cos x is this. So, cos hyperbolic x you will get if you replace x by ix. Okay. So, similarly tan x, cot x, again if you replace x by ix, you will get the cot tan hyperbolic x, cot hyperbolic x. Okay. So, this generally frequently used in solid state physics. So, just I showed you. So, now I got this relation where Tc and this lambda, okay, interaction energy constant, So, they are related. So, Tc depends on this material, and in that material how strongly they are interacting, this origin of this molecular field, how these dipoles are interacting. So, this it depends on the strength of that interaction, which is expressed by lambda. It is material dependent. Okay. So, now if you find out the magnetic susceptibility, so I think here I will use magnetic susceptibility, means at higher temperature, say at alpha equal to very alpha is less than 1, in this condition, so alpha is less than 1, in this condition if you find out, yes. So, here we have this relation, so here I cannot see magnetic field, but anyway. So, I think if I start from here, here alpha is, but alpha here I am missing, okay, that is why. So, originally alpha was this B, right. Now, if I consider this B A plus B M, this two term, okay, is now not B A is not equal to 0 in this condition. So, you will get that B M I will replace by lambda m, okay. So, it will give me two term, one is yes. So, I need space, I think I will so here what I want to get, so I will get two term, yes. So, from here I can write K B T alpha, K B T alpha equal to G J J mu V, right, into B A. So, B A I can write mu 0 H, B A I can write mu 0 H, and then plus another term I will get G J J mu V, J mu V lambda m, right. So, these two term so actually I think, yeah, I am not using the right one, m a j plus 1. I have derived, I think I should use some relation where m by ms, that and then alpha I am getting this one, but here anyway I think what I should do, this is the alpha term, and here, okay, from here also I can find out what I want to do. I want to find out susceptibility, susceptibility. So, here G j j mu v lambda m, okay, lambda m equal to so if I think I can where is my alpha? Alpha is here. So, I have to put I got okay. So, I think yes, I think this I have to start from here. So, this what we want to find out? We want to find out magnetic susceptibility. So, from here alpha is already there. So, I do not need to break it. So, what I should do? So, this alpha is this when we are applying magnetic field. Now, we have this m by ms equal to this. So, at alpha is very less than 1. So, this m by ms. So, m by ms is bjj. So, that will be j plus 1 by 3j. Yes, I think this into alpha. So, that I have to use this alpha. So, here I will get Gj j mu v by kbt okay, by kbt. So, this is another term. So, I think I have to this I can remove this one, this I need this one. So, then it has two term BA and another term I will get plus the same term I will get here, then lambda m, right. So, lambda m. So, then m I will get from here. If you simplify this one, so this j will go, okay, and then I have j plus 1 gj mu v. So, I will get and then if I multiply ms with this, see ms is n gj j mu v, okay. I multiplied this ms. So, m equal to this. Now, here then what I am getting, you see that j plus 1. So, let me write here j plus 1, okay, j plus 1, and then I am getting mu v was there, remember mu v is there. So, mu v was there. So, now another mu v, the square gj square, right, gj square divided by 3 kbt, right, and then BA means it is mu 0 h, and then plus the same term I will get same term up to this I will get same term, okay, except this lambda m. Instead of this will be lambda m, this will be lambda m, this one lambda m, okay. Okay. So, here you can see this mu 0, this term I can write n mu effective square mu 0 by 3 kb h by t and plus n mu effective square, then this here mu 0, here lambda, divide by here lambda divide by 3 kb and m by t, right. Here I will get m by t. Now, this here you can see this one is T c, this one is T c, this one is T c. So, this I can replace by T c, this I can replace by T c, and this one, as you remember, this is basically C Curie constant, this is C Curie constant. If you see earlier records, so you will see this will be Curie constant C, and then this my m. So, m is this side also. So, what I am getting? So, m, this one m. So, if I take m, I think I should write here. Let me write here. So, I am getting m 1 minus T c by t, but something wrong or what? Effective T c by t, okay, fine. T c by t equal to C h by t. Now, chi is m by h, chi is m by h, right, equal to C by t into 1 minus T c by t, right. So, chi equal to C by t minus T c, okay. So, this expression we found for taking this approximation alpha is very less than 1, means t is very high, okay. So, this is valid for t is very high, at least t is greater than T c. T is less than T c, it is not. So, it is for paramagnetic region, it is valid, okay. So, this is called the Curie-Weiss law, okay. So, this basically it explains the paramagnetic phase of ferromagnetic material, So, this very famous relation. So, that is the Curie-Weiss law, okay. So, I think that is all. Yes. So, I will stop here. So, I will continue in next class. Thank you.